Well, thanks for the invitation to speak. Everything I'm talking about today is based on a pair of papers that are already on the archive. So here are their IDs. I'll mostly be talking about the second one. So the first one is joint with John Baldwin and Ying. That was about Khovanov homology in the 2-5 torus knot. And the second one that I'm focused on is joint with John, as well as Zhenkun Li and Fan Ye. So to start, here's sort of a motivating question. What are really, in whatever sense you'd like to ask, three manifold groups? If I give you a finitely presented group, is it pi1 of some closed-oriented connected three manifold? And we know, for example, here's a theorem that we're all familiar with by now. Well, if Y is a three manifold different from S3, then the fundamental group is not the trivial group. Okay, that's a fairly fundamental result. But there's a conjecture, and it shows up somewhere in the Kirby list, but it's really motivated by gauge theory that says that if Y is a homology three sphere, but not actually a three sphere, then there's a representation of the fundamental group into SU2 with non-abelian image. So from pi1 of Y into SU2 like that. And so what this is saying, in general for a finitely presented group, the question of is it trivial is undecidable. You can't find an algorithm that will do it. For three manifold groups, you can, because we can recognize the three sphere, but there's still some amount of mystery in what the groups are. And so what this is saying is one way to detect it is to look at the SU2 character variety. Is it trivial or not? And so this is still open. I should mention a theorem of Raphael Zentner from maybe 4 or 5 years ago, that it's actually true if you replace SU2 with SL2C. Okay, but you might ask, what else can I detect using something like the SU2 character variety? Why is this phrased first for homology spheres? Because Floer defined instanton homology for a homology sphere to be some group which, as a chain complex, is generated by exactly conjugacy classes of these representations, the non-abelian ones. For technical reasons, he couldn't define it for rational homology spheres with non-trivial H1, but you could still ask the same question, at least, are there generators what you would like the instanton Floer chain complex to be? So here's a definition. We say that Y is SU2 abelian if these sorts of techniques fail to prove that the fundamental group is non-abelian. So if every homomorphism from pi1 of Y into SU2 has abelian image. Okay. What are some examples of this? Things where gauge theory might not distinguish it from something with abelian pi1. Well, the first possibility is that pi1 could actually be abelian. Lens spaces are SU2 abelian. But there are other examples. So Seifert fibered spaces, with base either say S2 and 3 singular points of order 3, or S2 with singular points of orders 2, 4, 4. And in this case, we need the order of the first homology to be even, or I guess infinite. This one, it takes a little more work to show, but these are SU2 abelian despite not being lens spaces. Other examples include lots of toroidal manifolds. Some that you get by splicing torus knot exteriors together in a particular way. I'll just say here, just to give a sort of well-known example, well-known if you ask the right people, but like a known example, I should say. If you do surgery on the -237 pretzel knot, 18 and 19 surgeries give you lens spaces. And if you take the thing that's right in the middle, slope 37/2, you get something toroidal, a splicing of a left and a right-handed trefoil exterior in a particular way. So these do exist in more abundance than, say, lens spaces. But here's a non-example, a really nice family of non-examples. So this is due to Kronheimer and Mrowka. It sort of fell out of their proof of the property P theorem, so it's about 2003. The theorem is, if K is a non-trivial knot in S3, and we take any rational slope R with the absolute value at most 2, then they proved that you could do R surgery on K, and this is not SU2 abelian. So you can always find a representation into SU2 that proves it's not something like a lens space. Maybe I should check. I don't know. Should I remind people what I mean by this Dehn surgery? Feel free to speak up if I've, maybe I'll just recall it anyway. So let's recall what I mean by Dehn surgery of slope R. Anytime we have a knot, here's our knot in S3, you can take a tubular neighborhood of it, and there it is, and it's got these two distinguished curves on the boundary. So one of them is a meridian, which I'll write mu. It bounds a disk in that tubular neighborhood, and the other one is lambda, which you can think of as bounding a Seifert surface for your knot K. And so P over Q surgery on K is just, we write it as S3 subscript P over Q, K. So we take the complement of the tubular neighborhood of K, and we glue in a solid torus. We had removed a solid torus to get to the exterior, but we're going to glue it back in a different way so that the curve mu to the P, lambda to the Q, where mu and lambda are these basis elements here. We want to fill that in with a disk. So we'll glue it to point times the boundary of a disk, like that. And you can do this for any rational number, and you get some manifold. And the point is that, for example, none of them are S3, because if they were S3, then that surgery would be SU2 abelian, because it would have trivial fundamental group. So anyway, another way of thinking of this is, equivalently, what Kronheimer and Mrowka proved is that there's a representation, well, I should say non-abelian representation of the knot group. So the fundamental group of the knot complement into SU2. And the fundamental group of Dehn surgery, well, you're just filling in this peripheral element with a disk. You're killing it in the fundamental group. So this is equivalent to saying there's a non-abelian representation that sends that element to the identity. Okay, so I should say if P over Q has absolute value in those two. So another way of restating Kronheimer and Mrowka's result is that there's a whole lot of different SU2 representations of knot groups. And when I say they're different, I mean they send all these different elements to the identity. They've got different kernels. So this is maybe this is a pretty striking result about knot groups. But you could ask, what about this rational number R? Why is it between plus or minus 2? So I should remark that this theorem can't be true. Maybe I should label it explicitly as a theorem, just, it's a little more, a little bigger than a non-example of something. But the theorem can't be true for slope R equals 5 because if you do 5 surgery on the right-handed trefoil, there it is, you get a lens space of order 5. It's 5 over 4 surgery on the unknot. It has abelian fundamental group, so you can't possibly find a non-abelian representation of that. But the question that they asked is, well, what about other slopes that maybe aren't quite so big? R equals 3 or 4. All right. So just to recap, the question here is, say for R equals 3, is it true that for every knot other than the unknot, every knot in the 3-sphere, if you do 3 surgery, you can find a representation of the fundamental group of that into SU2 with non-abelian image? So that's a way of detecting that, say, pi1 isn't abelian, for example. And so the main result of the talk, which is from the second paper I mentioned at the beginning. So it's joint with, again, with John Baldwin, with Zhenkun Li, and with Fan Ye from October, is that if K is a knot other than the unknot in S3, then there exists a non-abelian representation of the fundamental group of 3 surgery into SU2. And we you know, if we just proved about 3 surgery, okay, well that, you know, that would, you know, answer this question of Kronheimer and Mrowka. The case for R equals 4 was a little bit easier, and John and I did that 2 years ago. But it's also true for a dense set of slopes in the interval from 2 to 5, and this includes all integer slopes and half integer slopes in that range. I mean, the integers, there's only 3 and 4, and 2 was already known. But we also know it for 5 halves, 7 halves, 9 halves. I guess that's it. And then many others. All right, so the goal of the talk is to explain the proof of this theorem and the whole range of ideas that go into that. Any questions so far? Okay, let me just maybe mention just a quick corollary. So this isn't just abstractly interesting for its own sake. This was known, but now we've given a new proof. The corollary is that 3 surgery on a non-trivial knot is never a lens space. So this gives a new proof. It doesn't rely on previously knowing that fact, but if 3 surgery on some knot were a lens space, it would be SU2 abelian, and so this representation here wouldn't exist. All right. So what goes into it? The key input in this proof is a so-called framed instanton homology. Which is often written I sharp of Y. And this is a variant of instanton homology, which, if you prefer to think about Heegard-Floer homology, this behaves a lot like the simplest version of Heegard-Floer, the hat version. Okay. What it is very roughly is that it's the Morse homology of some functional in some infinite dimensional space. So a Chern-Simons functional coming from a space of connections on some principal SU2 bundle over a certain 3 manifold, whose critical set is very roughly the same thing as the space of homomorphisms from pi1 of Y into SU2. And this is like the one property that I'm going to use in this talk, is that is that we understand this, what are the critical points of this functional. There's a lot of work that goes into actually setting it up and defining it. But the point is that if y is SU2 abelian, then the right-hand side is very simple. It's basically a union of two spheres and points, and you can actually compute, say it's a rational homology sphere, that its homology is free of rank the order of H1. Okay. So, if you assume a non-degeneracy condition, which is not always satisfied, but often is, then there's a Morse-Bott spectral sequence, which gives you a rank inequality. Tells you that the instanton homology, the framed instanton homology, should be no bigger than this. And we know that it's always at least that big. This is just a basic fact about, it's got an Euler characteristic that's the order of H1 of Y, just like HF hat. So the key fact then is that the dimension of I sharp of Y would be equal to the order of H1 of Y. Okay, in other words, many SU2, so let me put it this way, just to summarize in a proposition, whatever this is, if Y is SU2 abelian, and if H1 of Y is cyclic, this is one way to ensure this non-degeneracy condition of order a prime power, then all of this holds. And so Y is what we call an instanton L space. Again, if you're more familiar with Heegard-Floer homology, we call a manifold an L space exactly when its HF hat has dimension equal to the order of its first homology. This is this is just exactly translating those words from Heegard-Floer into I sharp, and treating it essentially as a black box. But it has a nice property that because it's related to the fundamental group, when the fundamental group is simple in a nice way, this SU2 abelian property, then we know that we get an L space for free. And so the idea is, well, so let's suppose, just black boxing all of this, suppose that 3 surgery on a knot K is SU2 abelian. Well, the first homology of this is cyclic of order 3. That's exactly this condition here. So then what that says is K has an instanton L space surgery. And so by work that John and I did 2 years ago, we know that such knots are fibered. They're complement fibers over the circle, and they're strongly quasi-positive. Which is, also a nice property to have. But these are facts that would be very familiar to a Heegard-Floer homologist. So, I should credit all the people who prove these things in Heegard-Floer homology. We just, built very closely on work of Ojvat and Sabo, Gagini and Ni, Hedden. If you want to go further back, this certainly relies very crucially on work by Gabai, and you could credit a lot of people for this. But the point is, just by using this basic sort of black box fact, and knowing that knots with L space surgeries are very nice, we know already that a knot where 3 surgeries SU2 abelian has to be fairly restricted. It has to be fibered. It has to be strongly quasi-positive. Moreover, we know that the slope of any L space surgery has to be at least twice the genus minus 1. This is just a general fact about L space surgeries. And so that says that the genus of K has to be at most 2. And what are the genus 1 L space knots? Well, there's only one that's fibred and strongly quasi-positive of genus 1. It's the right-handed trefoil. So we rule that out very quickly, and we find that a knot like this has to have genus 2. Okay, and so the question we really want to answer, we started out with this question about fundamental groups of surgeries, but what we really want to know is what are the genus 2 L space knots? And this is open in Heegard-Fleur homology. This is open in instanton homology. I understand that some people are working on this, and we may be very close to an answer. The conjecture would be that the only one that exists is the 2,5 torus knot, but it's not proved yet, or at least not publicly that I've seen. So this is the question we find ourselves asking. What are the L space knots of genus 2? And it turns out we couldn't answer it completely. That's all right. We still sort of got far enough to solve the sort of titular conjecture. But let me say how we can answer this question partially. Say enough to actually get somewhere. So sort of a straightforward computation. There's a surgery exact triangle in Heegard-Fleur homology, and there's one in framed instanton homology that behaves essentially the same way. If we apply the surgery triangle, every time you go from n surgery on a knot to n+1 surgery, the rank changes by at most 1. And what you end up seeing is that if 3 surgery on K, where K has genus 2, is an instanton L space, then the 0 surgery on K has instanton homology, and I'm going to decorate this with a meridian. What this means really is that, like I said, there's a choice of bundle involved in defining instanton homology, and I'm asking for a non-trivial bundle that you can sort of detect by seeing it behave non-trivially on a meridian of the knot. The dimension of this is 6. You start with 3 surgery, you're at dimension 3. Maybe I can just draw a little graph of how it's supposed to behave. So dimension of I sharp of n surgery on K. And what we know essentially is that if 3 surgery on our genus 2 knot is an L space, so the 3 surgery on it has dimension 3, and you keep applying the surgery triangle over and over again, and the dimension just keeps going up. So it forms a sort of V shape and goes off forever in that direction. So when we're looking at 0 surgery, we have a 6-dimensional homology. And now we can actually relate this. This is framed instanton homology. This is some strange variant that was cooked up to work for things that aren't integer homology spheres, to work for things that have non-trivial finite H1. But actually, you can apply this to Fleur's original homology for things that look like a homology S1 times S2. So Fleur's instanton homology for admissible SO3 bundles, which is closely related, but just a slightly different construction, is going to satisfy the same thing. It's that when you take 0 surgery on K and equip it with a non-trivial bundle whose second steeple-winding class is dual to the meridian, that this is also 6-dimensional. There's a so-called Fukai's connected sum theorem that lets you relate the two. But the point is that this is actually reasonably well understood. So let's recall that K is fibered. So the complement of K, let's draw a little picture, say here, if we remove K from S3, well, it looks like a punctured genus 2 surface times an interval. And we glue the top to the bottom by some monodromy H, okay? So there's our picture of the complement of our knot. And we know a little bit of something about Floer homology, the instanton Floer homology of fibered manifolds. So let's say with monodromy H, as I've written there. And so we have some very difficult theorems that we can apply. One by Ivan Smith, and one by Dostoglu and Salomon, which says that says essentially the following: the dimension of this Floer homology of the zero surgery is actually the same. I mean, maybe I should write it a little differently. It's not just about the dimension. It's saying that there's an isomorphism between that and something which has the form C plus the symplectic Floer homology of almost the monodromy of H, plus another copy of C, and then we have to take two of these. Now, I'm going to write a little hat over H. And the theorem is that this is the case where H hat is a version of the monodromy on a closed surface. So we sort of capped it off. Okay. And I should add a little remark here. This only works in genus 2, for genus 2 fibered knots. Because what happened was, well, the result of Dostoglu and Salomon came first. They proved that for a fibered manifold, that you can describe the instanton homology of this manifold in terms of the symplectic Floer homology of the action of the monodromy on the character variety of the fiber. This is like some fairly, this is a very difficult theorem, but they're related to symplectic homology of some high dimensional thing. And then in genus 2, Ivan Smith proved that that symplectic Floer homology is actually the same as the symplectic Floer homology of just the monodromy acting on a closed surface. So what we know based on this is the following. Well, this was 6-dimensional. Here we've got a total of 4 dimensions from these factors here, and then 2 copies of this have the remaining rank, which is 2. So the corollary is that the symplectic Floer homology, whatever this is 1-dimensional. Okay, so we've understood something, some invariant actually of the monodromy of a genus 2 L space knot. And I should remark, again, the same thing. I was using sort of instanton homology as a black box here. I should say that the same is true for genus 2 Heegard-Floer L space knots. Via work of, in this case, work of Zhenkun Li and Cliff Taubes, where they prove that Heegard-Floer homology of zero surgery in some spin Z structure looks like the periodic Floer homology of the monodromy. And their theorem doesn't actually apply in genus 2, so you need a little trick to make it work. But everything I'm saying applies equally well in either theory. Okay. So, all right. The question is really, well, first of all, what is the symplectic Floer homology of this genus 2 mapping class that's supposed to be the monodromy of it's the monodromy of the fibration of the knot complement that's been capped off. You can think of this, if you like, as the monodromy of the zero surgery, which is itself a fibered manifold? Well, this is a generated as a chain complex by fixed points of the map H, which we can think of as circles in the mapping torus. So these are sections of the mapping torus of the map. Okay, and the differential counts pseudo-holomorphic cylinders, which are asymptotic to these in R times MH. So it's sort of a standard story in symplectic geometry that you can build invariants that look like this. But the key thing is, I would look at it and say, well, it's hopeless. How are we supposed to understand the differential? But the great thing that saves us is that it turns out to be entirely combinatorial. So in fact, using the fact that I mentioned earlier, that this genus 2 L space not K is strongly quasi-positive, that means that it's the binding of an open book for the tight contact structure on S3. You can use that to determine that the capped off monodromy H hat is a so-called pseudo-Anosov map. It has very interesting dynamics. Essentially, there's a pair of transverse foliations that are preserved by the action of H hat, and each of them comes equipped with a transverse measure that's either expanded or contracted by this action. This is the Nielsen-Thurston classification of surface diffeomorphism, says up to isotopy, every mapping class has a representative that's either reducible, it fixes some multi-curve, or it's periodic, so some power is the identity. And it's sort of amazing that the remaining case is that it has this nice dynamical behavior. But one thing that we know about pseudo-Anosov maps is that the fixed points of them are all in different Nielsen classes, as they're called. That means that these sections that correspond to fixed points are never homotopic to each other. So as part of his thesis, Andy Cotton Clay worked out entirely combinatorially what the what the symplectic Floer homology of any given mapping class has to be, and it turns out that for pseudo-Anosov maps, well, the differential just vanishes, and so this is free of rank the number of fixed points of the map itself. Okay, and so the conclusion we get, well, let me draw a picture. So we had our monodromy H, which lives on a punctured genus 2 surface. We fill it in to get a closed surface with this capped off monodromy. Okay, and we saw that, well, okay, first of all, there's going to be a point on this. We've just capped it off, and there's going to be a point at the center of that disk, which is fixed by H hat. Okay, but we also saw, using this work of Smith and of Dostoglu-Salomon, that the symplectic Floer homology has rank 1. So there's exactly one fixed point. If we call this point P, the conclusion is that P is the unique fixed point of the capped off monodromy, or equivalently, H has no fixed points. So this is a very striking fact, I think, about genus 2 L space knots, that, if they're not T25, they have to be pseudo-Anosov. And in that case, the monodromy of a pseudo-Anosov representative is automatically fixed point free. Okay. Now, why do we care about this? Well, here's the partial characterization I promised of genus 2 L-space knots. So let K be different from T25, and suppose it's an instanton L-space knot of genus 2. Okay. In that case, then I claim that there's a 5 braid, say, let's call it beta, with unknotted closure. Let's call that capital B, and braid axis A. Okay, here's a picture over to the side. Beta is our 5 braid. We've got braid axis A. Okay, like that. Such that this L space knot K is the lift of the braid axis to the branch double cover of S3 over the closure of that braid. And the branch double cover, since its closure is unknotted, is just S3. So that's what I claim is true about instanton L space knots, and that we can deduce using just this picture. In particular, well, given this description, there's definitely a symmetry of S3 that fixes K. That doesn't fix K. It fixes the lift of this braid axis. It says that K is a 2-periodic knot. So there's an involution of S3 which fixes some unknot and takes K to itself. All right. Okay, so here's the proof. Well, the genus 2 mapping class group is hyperelliptic. Everything in it commutes with some involution. So let tau be the involution of the genus 2 surface. Okay, that commutes with this capped off monodromy H hat that I indicated up here. Okay. Then, well, what happens if we apply the monodromy to tau of P? Well, tau, this involution is supposed to commute with the monodromy. Okay. And P is supposed to be fixed by the monodromy. So actually, we know that tau of P is fixed by H. So that says that both P and its image under the involution belong to the fixed set of H hat. But there's only one fixed point. Okay, that says that P has to be fixed by this involution. Okay, so we can draw a picture of that involution now. What does it do? You can just view it from the right perspective as putting this sort of on a spit and rotating it 180 degrees about that spit. Well, that's the involution tau. And since P is fixed by tau, it has to be one of these 6 points where we puncture the surface. So without loss of generality, it's maybe that one, just however we decided to draw things. And so what that says is, well, we can take the quotient by this involution and we can maybe remove the point P because that wasn't supposed to be part of the knot complement. So, right. We take the quotient by tau, then this quotient sends the mapping torus of our monodromy H, and I've drawn it without a hat now. H is just the monodromy of the knot complement. So how do we get that? We just remove this point P that we used to cap it off. And we get that this mapping torus is sent to, by this quotient action, the mapping torus of some 5 braid. In S3. Okay, what is that 5 braid? It's whatever gets traced out by these remaining 5 points that are fixed by the involution. Again, we remove this point P because it's not supposed to be part of the knot complement. We just did that to cap off the monodromy. But the reason for all of the work leading up to this was that once we don't know that the mapping class group of a punctured genus 2 surface is hyperelliptic. In other words, we don't know that a given mapping class will commute with an involution like this until we've used enough of this information to show that, well, when we cap it off, that capped point, the point at the center of that cap is fixed by the involution of the closed genus 2 surface. Then we can sort of remove it again and say, well, let's keep the involution and just lose the extra point. And so what we've shown is, again, that the mapping torus of H, which is just the complement of our knot K, is it double covers the mapping torus of this 5 braid. And why is it a 5 braid? Because that's supposed to be the fixed set. These 5 points are permuted setwise by that monodromy. And so we just let beta be that braid, and we let A be its axis, and that's it. So to recap, where are we? We wanted to characterize genus 2 instanton L space knots. So we said, well, we know that they're fibered, just as a general fact. What can we say about the monodromy? Well, the Floer homology of the zero surgery is related to this symplectic Floer homology of the monodromy. And so we're able to use that to say that when you cap it off, there's one fixed point. And when you cap it off, you're looking at a genus 2 surface, so it's hyperelliptic. And so you can then sort of take quotients by that action. And that's where this branched covering comes from. Maybe I should remark that there's the theorem of Wang and Zhou from 1992. Okay, that says that if K is not a torus knot, and if it has a symmetry other than a strong involution, so a strong involution means that there's an involution whose fixed set meets the knot in 2 points, which is not the case here. Okay, then K has no cyclic surgeries. So in particular, no lens space surgeries. And so what we've already shown is that 3 surgery on a non-trivial knot K can't be a lens space. Okay, this was a corollary I promised at the beginning, and I'm saying it already falls out from this characterization of genus 2 L space knots, because if 3 surgery were a lens space, it would be an L space. It would have to be an L space knot of genus 2, and now we have this characterization that all of these knots are 2 periodic, and the 2 periodicity means that you have exactly one of these symmetries other than a strong involution, so it can't be the fundamental group can't be cyclic. All right. Are there any questions about this result? This is sort of like the main thing, and it holds just as well for Heggard-Floer L space knots, like I said, using the work of Li and Taubes. All right.
Yeah, I have a general question. Can you remind me the definition of instanton knot L space?
Yeah, so an instanton L space knot is one for which some Dehn surgery produces one of these instanton L spaces. In other words, something for which the framed instanton homology is as small as possible.
Okay. Okay. And in particular, the third surgery.
Right, right. That's what I'm interested in here is the three surgery. Okay, so I've got only a few minutes left. I want to sort of sketch the rest of the proof. Okay, so let's suppose that 3 surgery on our knot K is SU2 abelian. Okay, then K is a genus 2 instanton L space knot. Okay, so remember that means we have this picture where there's a there's some fibrate whose closure is unknotted, and we can write this well up to isotopy. Since its closure is unknotted, we can redraw it a little bit. We can say if B was the closure of that braid beta, B is an unknot, and A is some mass that may not be braided in the complement of B. And so our picture of K, well, we take the branch double cover of B and we lift A to that branch double cover. And so the picture, maybe I should have drawn this on the last page. Well, we take 2 copies of that tangled mess that I labeled with A, like this, and we join them together. That's what the knot K is supposed to look like. Okay, so in particular, it's 2 periodic. And now we apply, well, I've heard many things called the Montecinos trick. As far as I know, this is an example of it. The point is that this symmetry, well, there's the symmetry of the complement of K, and if you try and do Dehn surgery on K, you can often fill the you can fill it and extend the involution of its complement across the surgery solid torus. And so what it'll tell us in this case is that if we do 3 surgery on K, that's the same thing as the branch double cover in, so we do P over 2Q surgery on the knot, well, sorry, this should really be P over Q. If we insist that P be odd, then we can extend the involution freely across the surgery torus. This is the same thing as doing P over 2Q surgery on our knot A. We lift the knot B to that surgered manifold, so I write that B bar, and we take the branch double cover of that lift. And so what we have here is LP comma 2Q, since A, the braid axis, is unknotted. Okay, so we have, there's a knot J sitting inside, in this case, L3 comma 2, such that its branch double cover is just diffeomorphic to 3 surgery on our knot K. In other words, we've taken the surgery of K and used it to find a surgery, to find a symmetry of the surgered manifold. And let me just say, then we take, since the 3 surgery is SU2 abelian, one can show that the instanton knot homology, which I won't define, of this knot, and when I write that, you should again think of, in Heegard-Fleur homology, the simplest version, H of K hat. This is as simple as possible. In other words, the dimension is, in this case, 3. Okay, but then this, just like H of K, this invariant is known to detect through some Alexander grading, it's known to detect rational fibredness. In other words, whether the complement of a knot is a fibered manifold, and also the rational genus, which is, in other words, the genus of a fiber of that fibration. And so if you do a little bit of computation using, in fact, known facts from Hegardt-Fleur homology, it turns out that the complement has to be both rationally fibered and of rational genus 0. It has to be a solid torus. And so what's the branch double cover of this knot J? Well, if the complement is a solid torus, then when you take branch covers, you're going to get a lens space. So that says that the 3 surgery, this branch cover, is a lens space. And we already knew that couldn't happen. So that's a contradiction. And that's enough to finish the proof. Maybe let me just mention briefly that what happens when you try to generalize this to other slopes that are strictly less than 5. If you're a lot more careful about this part of the argument, about thinking about the instanton knot homology, you can add a lot of extra slopes in, which is where the others come from. But it's all just variations on this idea with some more details to work out. Anyway, I'll stop there. So thanks everyone for your time.
Okay, well, let's thank Stephen. Does anyone have any questions?
Yeah, I have a question. Let's see.
All right.
So you produce all these SU2 representations, which are killing slopes, like this 10 set of slopes between 2 and 5.
Right.
I'm tempted to say you can find a curve, a nice curve, an algebraic curve, and which contains it. And so somehow you're going to get all slopes between 2 and 5. So what goes wrong with that?
I should mention, okay, this is totally reasonable to conjecture, and I really think it's true, but these methods don't quite work for it, is that, S3, you do R surgery on a knot in S3, and it should never be SU2 abelian if the slope is strictly less than 5. Now, these methods only work, unfortunately, these require to have the form R equals P over Q, where P is a prime power. And the reason is that I needed this non-degeneracy condition to get it off the ground, to assert that SU2 abelian implies L space. Because then we know that this Chern-Simons functional is more spot. And if it's not a prime power, then it may not be. There's actually a precise description in terms of the, well, I guess this is one of your papers based on the roots of the Alexander polynomial. So, Kronheimer and Mrowka's argument was very different, in part because they didn't have framed instanton homology back then, but also because they just sort of took the character variety for 0 surgery and manipulated that directly using perturbations of the Chern-Simons functional. It certainly should be true, though. I mean, I don't expect there to be any counterexamples.
The fact, do you expect that the trefoil is the only knot for which R equal 5 is SU2 abelian?
Yeah, I do. Well, so one thing, if I go back up to the top, there was this conjecture that the only genus 2 L space knot, wherever it is that it's only T25. And so if 5 surgery were an L space, just using this genus bound, 2G minus 1 has to be at most 5. In other words, it would have to be surgery on the genus 3 knot, and a genus 3 L space knot as well, which there probably aren't that many of them. So yeah, I mean, I do believe that it should extend to 5 surgery, but I can't prove it. And maybe another thing I should mention about these methods is that because we have a 5 grade, there's this funny fact that this knot that we're taking the branch double cover of represents 5 times a generator of H1 of the L space. And we really need the knot to be primitive in homology to generate the homology. So somehow these methods also don't work when the numerator of the slope is a power of 5. So we need something completely different in that case, but I still think it's true.
Okay, well, I have one possibly naive question,
Right?
which possibly has a yes or no answer. It seems to me that these SU2 abelian manifolds are sort of playing the role of strong L spaces.
Yeah.
I assume they're not exactly the same thing,
Right. Well,
conjecturally or otherwise.
they shouldn't be. I mean, we've got this list of known SU2 abelian ones, and as far as I know, right, it may be true that every strong L space in the Hegardt-Fleur sense is the branch double cover of an alternating
Yeah.
knot. Now, so the toroidal examples I know are branch double covers of alternating knots. That's something that Raphael Zentner proved. Lens spaces are, maybe among these Seifert fibered manifolds, there are some ones, but maybe I can also add sporadic examples. So you can take the branch double cover of 818 or 10109 for some reason. These are hyperbolic examples, and I don't think this is alternating. So it probably isn't a strong L space.
I know that 109 is alternating.
It is. Oh, okay.
Okay.
Well, I still don't think they're the same. I mean, branch double covers of alternating knots certainly don't need to be SU2 abelian. So for all I know, it's possible we have inclusion one way, but not the other.
Okay. Thanks. Okay. Well, if there are no other questions, let's thank Stephen again.
All right. And thanks for having me.
Yeah, great talk.
Yeah.